Hi, everybody. So, in this section, I want to talk about the order topology. So, whatever that means. So, the first thing I want to talk about, so this is it's a topology that we can associate to any ordered set. So, recall that an ordered set is a pair, so it's a set, I want to say X now, together with a relation, which I'll call less than. This is a set. This is a relation. Which is kind of, very loosely just a way of relating different elements of the set X, satisfying sort of two things. One is that, maybe I should also specify further, this is a totally ordered set. If you guys have maybe seen partially ordered sets before. So a totally ordered set is one in which, for all elements x and y in X, one of the three things is always true. Either x is less than y is less than x, or y is equal to x. So this is just a way of saying that any two elements are related in some way by this relation less than. And of course, we sometimes say x is less than or equal to y if either x is less than y or x is equal to y. It gives an equivalent type of relation. So those of you who are taking real analysis right now, or particular real analysis with me, you'll note that we have also just talked about these things recently. In particular, the real numbers and the rational numbers are both examples of ordered sets or ordered fields. So the cool thing here is that, why are we talking about it in a topology class, is that any ordered set, no matter what it is, has a natural topology determined by the order. And fittingly, we call it the order topology. The order topology on the set. So ordered sets are really nice because they let us talk about intervals, whatever that means. These things like A, B, and so on. It's a set in which this notation kind of makes sense. Defined in the normal way, I defined this one last time, and this one, I actually kind of implicitly defined all these before, and hopefully you've seen this in any given subject before. If not, let me know, and I can expand on that a little bit more. So, what is this topology? Well, I'm going to specify it on a basis. So, has as basis the following subsets. All intervals of the form A to B which we know to be, all little x and big X, such that this is true. It has 2. So if there is a smallest element of X, it has the following. All intervals A naught B, where A naught is the smallest element of X. If there is one, there doesn't have to be. I should say, if it exists. Likewise, we can imagine that if there's a biggest element, I want all intervals that are kind of closed on the right-hand side at that biggest element. So this would be A to B naught, where B naught is the biggest element of X, if it exists. And that's it. So I claim that this generates a topology, that this is actually a basis. But I'm lazy, and so I want you guys to check that for me. This is kind of straightforward. Check. This is actually a basis. You know how to do that by now. So it's clear when I'm talking about just the real numbers, if X is the reals with the usual ordering, this gives the standard topology. Almost by definition, right? There is no biggest or smallest element of the real numbers, and so the only thing we have would be this one right here. But all intervals of that form, by definition, is the, come on, zoom in, is the standard topology. Oh, my nose is leaking still. We can have the extended reals. So this is the reals union two elements, which I will call positive or negative infinity. Likewise, you could just maybe add only one of the two. This gives us a standard topology. So, I should say, the order topology on this set, the extended reals, is a topology. We think about it, it's just a real line, but I've added in 2 extra points here at positive and negative infinity. And it's a way of adding in those points in a way that's consistent with the usual topology. So now I just say, well, what's a neighborhood of positive infinity? Or what's an open set containing positive infinity? I think I've already defined neighborhood. It's just some set of the form, some real number, infinity. There's a kind of cool thing we'll see maybe a little bit down the road. Maybe I only added in one infinity. Like I'm just adding in some point that I consider to be infinitely far away from every other point. I'll call this x tilde. I'm adding in one point, which I consider this to be infinitely far away. You can think about it as if I considered positive infinity and negative infinity to be sort of the same point. What would this resulting topology look like? So a neighborhood of this point would be something like this. It'd be like a union. So I'll abbreviate neighborhood as NBHD. Which we take to mean some open set containing the point. A neighborhood of infinity of this weird new point, I'll do a little tilde there, would be something of the form negative infinity to some number, union some number a to positive infinity. Or maybe b is strictly less than a. This is not exactly the order topology anymore. We're kind of leaving things behind for right now. So what is this weird space? Well, it's something actually super familiar. If I add in an extra point at infinity and consider this point to be the same as this point, well, I might as well just draw them as the same point. And in fact, this is actually, geez, my handwriting is the worst. This is actually, in a sense, equal to, in a topological sense, the unit circle. Whatever that means, I should say, like equal. We'll see, we'll have the words for this soon, but equal will become homeomorphic. And it's not actually really the unit circle, or maybe it is, up to homeomorphism, but it's something called the real projective line, RP1. But we'll get there. This is just something that happens if you to say, well, what if that's the same point? What happens then? As another example. So you'll find that I kind of like to spend most of the time with examples in this class. The material is objectively difficult. It is abstract. That is okay if it feels too abstract at first. It does for everybody. The best way to get used to topology is just to arm yourself with a horde of examples. So we use this textbook, Topology by Munkers, as a canonical book. Another really good book that you can find for this class is called Counterexamples in Topology. Actually, one sec, I'll take a picture of it. All right, I'm back. One sec. I can take pictures of things. It's a great little book. It's one of the Dover textbooks, so it's like, I think like $10 or $12. And it's got like a horde of examples, just like I said, like hundreds of examples. Occasionally I'll pull one and ask it on a homework exam or a homework question or as an exam question. One of my questions on the final last year for this class was about a construction called Cantor's leaky tent. That's not an example for this particular section. This is just kind of a random thing I remembered about. This is not at all something I would require you to buy for this course. But if you find that you like this and you find that you like having extra examples, this book is literally just examples and counterexamples. Yeah, it doesn't really, there's like, I think 5 pages of actual expository material and the rest is just examples. What was I talking about? Right. So we've seen some bases for R2. The plane, right? So these are just all ordered pairs of real numbers. So we saw we can have a basis consisting of open balls or a basis consisting of open rectangles. But I'm going to define an order on this set, which then means it naturally has an order topology. So I'll give this order, this is called the lexicographic ordering, or the dictionary ordering. dictionary or lexicographic. Which says that x1 y1 is less than x2 y2 if the following happens. If either x1 is less than x2, or if x1 equals x2, then y1 is less than y2. How do you think about this? Why is it called the dictionary ordering? Well, we'd say, apple is less than banana in the dictionary. I don't know how to spell banana. But aardvark is less than apple. In the sense that we'd first look at the first coordinate to see, if they're equal. So here, A is less than B, right? A comes before B in the alphabet. But here, well, they're the same, so then I look at the next letter. That's why it's called the dictionary ordering. So what do the open sets look like in this topology? Well, they look like, one example would be something that's just a straight line. For example, if I had maybe 1, 1 to 1, 3. That's an example of an open set, right? Likewise, I could have something that's, let's say, it goes all the way up, and it comes back up again. This is completely, not to scale. Maybe this is 3, 1, and this is, wow, it's really awful not to scale at all. And this point here would be 4, 2. So this would be, I called this interval, the interval from 1, 1 to 1, 3. And I'd call this one the interval from 3, 1 to 4, 2. So those are both examples of open intervals. But there's no biggest element or no smallest element here either. So we only have these open intervals. What's another example? Let's say I could look at the positive integers. Maybe I'll just write this as like n with the usual ordering. Well, this is an ordered set, so I can define an order topology on here. So which sets are open? Well, all intervals of the form n to m all natural numbers between n and m. So these are always going to be open. You'll note that in particular, if I look at n to n plus 1 for any natural number, this is always going to be empty. There are no natural numbers between n and n plus 1. And if I look at something like n minus 1 to n plus 1, the only natural number in that interval is n itself. And that's open now, because I said so. But the cool thing is, once you find that singleton sets, so I'd call this a one-element set, it's sometimes called a singleton. Once those are open, everything is open, because every subset is a union, arbitrarily so, maybe, of singleton sets. So even though we can give this a topology, the order topology, this ends up just being the discrete topology. That was one of those ones we defined in the very beginning, which is a topology in which every subset is open. So it's not like an interesting topology. We can do it, but it's not useful. Another one that'd be kind of cool to talk about in the sense that I'm going to define it and then not do the work, and I'm going to ask you guys to do it. So look at the set x is, I'll do 1, 2 cross the natural numbers. So this looks like all ordered pairs. I just spit on my iPad. Oh, nice. Good job, Brian. All ordered pairs of the form, let's say x, n, where n is a natural number, and x is equal to either 1 or 2. And I give this thing the same dictionary order as before. Right? It's just ordered pairs of things. I can define the exact same type of order. So the weird thing is here is that most of the singleton sets, most of the 1-point sets are open, but not all of them. So there's some 1-point sets that are not empty, or sorry, that are not open. Are not open. Find one. So in particular, if there's some singleton set that is not open, then this does not have the discrete topology. So that's something I want you guys to try to do. This is just a fun little thing. If that's not fun, I'm sorry, then think about it as informal homework. All right, I'll see you later.